Thank you, Bimalendu, and let me thank organizers, Subhasish, Nirmalya, Tarak, okay, and Bimalendu, who has introduced me, for inviting me to be here and discuss something which we have done recently. So this is discussion meeting, and that's why I have kept the work which I can discuss. I can take your feedback, okay, and students also can give their feedback, PDFs, okay. And it is unpublished work. I am going to present only one work, okay. So I want to have your feedback, particularly theorist. So this quantum signature of photons with orbital momentum, the work started with Shashi Prabhakar. He is there now. Earlier he was a student, and now he is faculty at PRL. So he started down conversion of OM beams, optical vertices. That's how it started. We wanted to see the signature of OM in down converted photons. After that, Nigel started studying photon statistics of OM photons, photons carrying OM, and he observed there are some changes, and we could explain theoretically. Anindya helped him to explain it theoretically. Why G20 values, which are they are different when you use vertices compared to Gaussian beams. If it is L is equal to 0 Gaussian beam, G20 values are different compared to when you are using optical vertices. You get heralded single photon using SPDC, and you measure G20 for that. It is slightly different, and as you increase the order, it changes. Rather, it pure single photon, it goes towards less single photon nature. G2 value increases. 0.01, it starts with 0.01, very small value for Gaussian beam, and as you go towards higher order, 0.02, 0.03, and that's how it's. So we could explain that and published in Journal of Modern Optics. Then Sarika, Nizil is now doing a postdoc at NIST, and Anindya is doing senior researcher at NUS CQT. And Sarika, she has finished her PhD, and now she will be moving to Germany, Fraunhofer Institute for postdoc in quantum communication. So we wanted to study further this quantum signature of photons with orbital momentum. So I asked Sarika to do some experiment to see whether this OM, it's a mode property or photon property. It's at the mode level or at the photon level. That's what the idea. So we wanted to do HOM experiment and see that whether it is photon property, orbital momentum, or mode property. So, and this result we got 2 years back, okay, but it's still not published. And I heard Jubin's talk, okay, Jubin is not around. So I heard Jubin's talk, and he was talking about this spin orbital separation and all those things. So I discussed with him online. He was very excited to see the results, and he said straight away you can go ahead and write and submit in Optica. So, but there is a twist. He was very impressed with the results. The results were very clean, experimental results. He said there is no need of doing theory. Experiments are so clean, and you can go ahead and write and submit in Optica. So I started writing, but there is a twist. Why we have not yet published this? I will tell it at the end. Okay. So these things have been already talked about. Pointing vector, you can, for electromagnetic wave, you can say E cross B. And then, yes, you can always write in terms of P by C square. So angular momentum density you can define for electromagnetic waves, and that's how you define the total angular momentum. And total angular momentum you can write as L plus L, orbital momentum and spin angular momentum. It has already been talked about by Nirmalya and Jubin. So this pointing showed that for a beam, circularly polarized beam, you can take this ratio, angular momentum and energy. And this comes out to be 1 by omega. And if you go to photon level, so you just multiply by h cross. So upside also numerator, so it becomes h cross. So that's how it came, angular momentum for the spin polarized light. And then Beth did a very fine experiment. But before Beth, our own C.V. Raman, he published a paper in Indian Journal of Physics, very smart fellow. First he published 1931 Indian Journal of Physics. Then he communicated to Nature, same thing, giving reference of Indian Journal of Physics paper. And he was observing spectroscopy person. So he was observing gas molecules he was studying. And in spectroscopic lines, he could see the signature of this spin angular momentum. And he told that without spin angular momentum, these lines are, this signature is not possible. So it was published in Nature 1932 as well as 1931. Then Beth did the very fine experiment to experiment basically, and that was also experiment only. Spectroscopy was experiment only, but it was not direct observation. Beth did the direct observation and passed this circularly polarized light to the half wave plate. It changes the helicity, so 2H cross now. So this could rotate, and very fine vacuum he created. It was hanging with very thin wire, frictionless wire, so he could measure the rotation. What is the rotation? That's how he concluded that there is spin momentum with the light. And if you have field, that was the plane wave basically, but if you have field like this, having azimuthal phase, and then you calculate the angular momentum and energy, so you get this kind of ratio. So that was given by Allen and company, Leigh Allen and company. So again, for photon, if you go, you just multiply by H cross, so you know energy, and that's how it comes LH cross and plus minus H cross. So that's how it comes orbital angular momentum of the photon. So that's what they pointed out in 1992. After that, this field has exploded from 1992 when they observed that this light can carry orbital momentum along with spin momentum. So, but there is problem like when you quantize, can you quantize that each photon will have LH cross of orbital momentum if you have order L. Not on average each photon. So you have to quantize the field and see. So our own guys, Arvind, Professor Chaturvedi, I am missing, he should be here. Somehow I don't see him here in this meeting. Professor Chaturvedi and Mukunda, they wrote a paper, Properties of Spin and Orbital Momentum of Light. So what they write, while the quantum counterparts, this L cap and S cap, these operators of L and S, go over into bona fide observables, they fail to satisfy the angular momentum algebra, making their interpretation as orbital and spin operators untenable at the quantum level. So it's very recent paper. So that's how they conclude. They have done detailed theoretical calculation. I'm not theory guy, although I have read, so I could not follow exactly everything. It's involved field theory and all. And then summary and conclusion they write, with our improved understanding of the algebraic properties of these operators, orbital momentum, spin angular momentum operators, in particular that they are not angular momenta, it seems preferable to expand the OAM to optical angular momentum. The terms spin and orbital angular momenta of light are thus misnomers. So that's how they conclude. Okay. And optical angular momentum, I think Landau leaves it. This Bimalendu pointed out, he also used optical angular momentum. So that I think they cut the OAM thing, optical momentum from there. So, and around same time, this archive paper also came, Quantum Spin Operator of Photon by Jubin. He has already talked about this paper yesterday. And they conclude our work resolves the long-standing issues on the decomposition of orbital and spin angular momentum. If it is theory question, please don't ask. I will come to the experiment. Yeah. Yeah.
Okay. What I'm saying is all the claims by Michael Brady and others, that's wrong. That means you can break it up, this pointing vector into two parts, orbital part and spin part. All that is wrong. That's what Subhasish and others, they are claiming, and Mukunda, they are claiming in that paper. I'm not familiar with this paper. That's the reason I'm asking.
So they have published two papers. They are saying it doesn't follow angular momentum algebra. So it's not like quantum mechanical.
No, this last sentence,
operator.
Wrote, the term spin and orbital angular momentum of light are thus misnomers.
Yeah, that's what they conclude. You can read the paper, and yeah, you have to read the paper carefully. So that's what. And then Jubin, we saw that our defined photon spin and OM operators satisfy the standard angular momentum commutation. So the same time two papers coming, it's slightly confusing whether they are really quantum mechanical operators, quantum mechanical observable, or just or you have to see only a total approximate.
Okay, now you said that we can have some comments on this.
Yeah, sure, sure, sure.
Sometime back, Leok also was talked about these things, saying that there is a problem with the definition of this angular momentum, whether it is spin or orbital. If you go from classical electromagnetic theory to the high energy physics way of doing it and the optics way of doing it, so there is some discrepancy between,
Yeah,
because different people are defining it in
different
ways,
ways, yeah.
and this quantum mechanical way of doing it
Mm.
shows that there is a discrepancy. It's all already kind of, people have talked about it in bits and pieces, but I remember Leok in one talk said that they were trying to unify the
Trying to unify,
definitions
but still it is not unified. Otherwise, this paper now it is published in 2021 or 2022, Jubin Jacob.
No,
It is not.
unified in the sense of the discrepancy between the definitions of how angular momentum is defined in an area of research.
Yeah.
Whether it is high energy physics or optics or other quantum mechanics. That they are trying to put it together. I am not sure whether it is done or not, but there was a
It's-
People later on by Leok on
yes,
dual electromagnetism and
yes,
so on and so on. So they have clarified many issues with
yes,
possibly
But quantum mechanical, if you go domain, quantization is still not clear. Like,
from the quantum formalism and from the he calls it dual electromagnetic formalism.
yes.
So he put that they are
But it is,
in parallel.
my question is that is still classical electrodynamic theory kind of thing, but quantum I am not sure whether they have done it.
he has commented on that. It's not clear. He himself is still not clear. He has commented on that. So Bleak paper I have been following because of these issues. So if you see here, but if you do experiment, you can see this is when a beam size is larger than the particle. You can transfer either orbital momentum, you can see how it is moving around, or you can transfer the spin angular momentum. Okay. So yesterday, a day before, Ian was showing pictures, and his beam size was smaller than the particle. So their OAM and spin they get mixed up. But if you have particle size smaller than the beam size, okay, then you can see these specs separately: spin angular momentum and orbital momentum. You can have linearly polarized OM beam, and you will see this effect. Orbital thing. If you take circularly polarized light without orbital momentum, you will see this effect. So you can see that classically you can transfer and you see this effect. And light is photon only. So photon should have. Why it should not have orbital momentum and spin angular momentum separately? Because you are transferring, you can see that effect. So let's go to the next slide. So before I go to the experiment, some general introduction, how do we make vertices in our lab, okay? So they are the three techniques, we have used all the three techniques, but making vertices with this technique is slightly tricky. You have to have open cavity, and for particular cavity, for particular wavelength only you can make, and it gives very nice vertices, but you have to have open cavity laser, then only you can make, and you can use this. First you have to generate higher order HG modes. If you are using open cavity, you have to put crossfire something, you generate higher order modes, then you put the cylindrical lenses, and you can convert higher order modes or HG modes to the LG modes. So that's how they make. This is HG modes, and then you can make LG mode. Or simply when LG mode you take radial index as 0 and azimuthal index 1, 2, 3 integers, you call optical vertex. Generally when we say optical vertex means radial index is 0, but they are LG modes. So that's how you make, but in general we are not using this technique in the lab. We use computer generated holography, that is and for that we use the spatial light modulator. We transfer these holograms, we generate in computer and transfer to SLM, and this kind of fog grating, if you pass this plane, like plane wave or Gaussian beam, and it has to pass to this branch point, it will you will have diffraction. And first order, if it is like two lines combining into one, in first order, this is L is equal to 1 corresponding first order diffraction, you will get first order optical vertex. So that's how you generate. And other technique we also use is spiral phase plate. It gives very clean vertices. You just pass your Gaussian beam through the spiral phase plate. Already Gautam has talked about, and you get very clean vertices. But spiral phase plates are not available for other orders on particular wavelengths. So most of the time we use SLM. Sometimes we use where spiral phase plate is available. Sometimes they write it vertex length. So wherever it is available, we use this because very compact and gives very nice vertex. And this is the technique. Once you have generated the vertex, you can measure the charge of the vertex because you have to measure this order and what is the sign of the topological charge associated with the order. And very simple technique, just put a tilted lens, normal lens which you use in the lab, okay, convex lens, simple, just tilt it and you can measure what is the vertex charge and order. So if it is +4 and -4, this you can see the orientation 7, 10. You can take any order, okay, and you can measure. So that's how we have done. These are the theory results. These are the experimental results, and like depending on how many lobes you can see here, you can find out the charge. But when you go to the quantum thing like down converted photons, generally this is the technique we use to find out the charge of the vertex or order of the vertex. What we do, suppose here this L is equal to 0, you have generated these vertices. These are the diffraction orders, +1, 0, -1, these are the diffraction orders. And these are the like orbital momentum thing, L -1. So first order you get L +1 when you have L is equal to 1 corresponding to L +1 hologram. And now you have generated, now you want to measure the charge of the order of the vertex. So again you pass through the hologram. So suppose it is L is equal to -1 and -1 is coming. So you will get 0th order in the first diffracted order. Okay, it is +1 coming, -1. So you will get in first diffracted order you will get Gaussian beam, L is equal to 0, and you can couple to the single mode fiber because single mode fiber carries Gaussian beam. So that's how you measure. Different charges go, and first order you have to convert like different holograms on SLM. You can keep on changing. It is computer interface, and then you can keep on like coupling with your single mode fiber, first diffracted order what you get. So that's how you measure what is the order of the vertex and charge of the vertex. Yeah.
Can I just ask one?
Yeah, sure.
So this, but the higher order modes are not the eigenmodes of single mode fiber. It is a Gaussian beam. So how are you trying to push it in the?
So that's what you convert into single mode, Gaussian beam, then only you couple, not higher order modes. This hologram will convert into this Gaussian beam.
Oh, this is after that.
After that, huh? You see that, this is after that. It's after that, after making the Gaussian, after converting, but it will not convert. If you are using -1, it is 1 when your incident L is equal to 1, then only it will have first order 0. So depending on, you can keep on changing and you can keep on separating the OM.
So the power coupled will tell you how much of.
Yeah. That's how you measure.
So -1 will convert only +1.
Yeah, in first diffracted order, yeah. So you have to keep your single mode fiber coupler at that position. So now this is classical experiment. You can pass your L is equal to 1, L is equal to T to this optical vertex, and you can see that beam splitter, you will single tilted lens we are using here to see the charge. So you will have L is equal to 1, L is equal to -1 because you are reflecting, basically charge is conserved because you are changing the coordinate frame. So that's why you say this inverse thing here, okay. So otherwise both side you get charge 1 only. So this is classical experiment. Your beam is coming, charge is equal to 2, so 2 - 2 or 2, charge is conserved. So it splits into, you always observe 2, charge 2 for the beam. Let's see now, we'll do the first, we go to, before going to HOM experiment with these 2 photons, we'll discuss what is the HOM Hong-Ohm Mandal interferometer. So this is the paper which introduced this 2 photon interference. Here you will see the beam splitter, and that's what R and T, this is for this beam splitter basically. So you get down converted photons, 2 down converted photons, this is the filter, and then they go here, and then you measure the coincidences. Okay, these are the coincidence counters, okay, these 2 detectors, and these are the coincidence counter. When they are like in a very short interval, when they are coming together and they are almost they are similar in every in all its behavior, and they're coming together, so you will get the deep, no coincidence, because 2 photons, these 2 photons either go here or there. Okay, this you can see here, if R and T is equal to 0, equal R and T, reflectivity and transmittivity, so this factor will become 0 here, and this is supposed to be 50-50 beam splitter, and so photon will go here or here, and since only one port is getting photon, coincidence will be 0. When you have one photon in both the detector, then only will have coincidence. So that's what happens. And this experiment was used to demonstrate 2 photon indistinguishability, measurement of length of photon wave packet, that was the first, and producing maximally entangled states. You can use very, you have to use like wave plates along with this, and you can do maximally entangled polarization states. Then quantum metrology, of course, this is 2 photon interferometry, and quantum information processing and quantum communication through entanglement swapping. So it has a lot of applications. It's just a very basic experiment done for science, basically basic science, but it has a lot of applications. This is used in many applications. So that's what you observe. This is coincidence count, and you can see here like your spectral width and time, this delay, okay, that will govern your coincidence count, or the width, this width, that's what it will govern. So delta omega delta tau, time interval of 2 photons, if they are together, delta tau is equal to 0, they are coming together, you will see that this term will become 1, and 1 minus 1, you will have 0 coincidence. They are coming together, and delta omega is also very small. So delta omega here, but we are we define our band pass filter in terms of wavelength, so it's inverse of that. So you will see when it is 10 nanometer band pass filter, so you have a full width half maximum is 65.61 micrometer. You can convert this into delay also by multiplying with the speed of light. Okay, you can convert into delay. Okay, just use the speed of light and you can convert it into delay. So, and this, when you are using this smaller band pass filter, it becomes larger, full width at half. So it shows like temporal and spectral distinguishability. You can measure using this HOM experiment. Yeah.
In the Hong-Ohm Mandal experiment, what is the information contained in the width of this peak?
Width of the peak, you see this, means spectral bandwidth, how much, that's what, you can see that. So it contains the spectral band. How much they are similar in spectral, yeah. So this is the quantum experiment with now photons carrying absolute momentum. So you see here, this is type 1 BBO, okay. So you make this down converted photons, 2 photons here, and you take them like this whole part is HOM, okay. So 2 photons coming to beam splitter, and one side you are just dumping, okay. And this is 2 0, you measure the coincidences, and you have 0 2 and 2 0. So you take these two photons here at this port, okay, and pass through the spiral phase plate. So 2 photons coming together, and you pass to the spiral phase plate. So you get like second order, first order, you can change the spiral phase plate as I talked, and you can get different orders. Now we pass to the second beam splitter, and we divide and measure in coincidence. Okay, we do the coincidence measurement after splitting through second beam splitter, and we are measuring like OAM. Okay, these SLMs are there, SLMs are there. Okay, these SLMs are there, and we are measuring the OAM, the method I told, by single mode fiber. So we get very interesting result. You can see that when you have SPP2 you are using, so you see these coincidences are maximizing when 1, 1 for 1, 1. Okay, so means photon you have made SPP2 you have used, but what photons are carrying orbital momentum 1h cross. You have 2 photons, and in coincidence you are getting maxima at 1, 1. Okay, and we are using SPP2. So it's not mode property, it's photon property. That's what it's showing. Same way, if you use SPP -2, you will see -1, -1. These are the, you should have written like L1, L2. So basically this is L, orbital momentum. Some symbol, different symbol they have used, but this is orbital momentum. So when orbital momentum is 1, 1, you get maxima. When you are generating this 2. Okay. And same way, if you have -2, if I put SPP -2, you will get -1, -1. So means photons are distributing the orbital momentum. And you can use SPP0, it's just confirms like 0, 0 Gaussian beam. Okay. And -1 also, 1 also, because fractional charge as it propagates, it becomes like integer. So most, if we have 0.1, it will go to 0 or 1. So you will see here, if we are using SPP1, it goes to either 1 or 0, because 0.5, 0.5. So orbital momentum is being carried by the photon separately. So that's what these results, we confirm with 3, -3, everything. It's coming very nicely. We were very excited, and it was repeatedly we were getting these results, very clean results we were getting. And then even without beam splitter, second beam splitter, we are not putting any beam splitter, just 2 photons are coming. And we wanted to measure the spectrum, and we get peak at, suppose SPP2, we are using like spiral phase plate of L is equal to 2. So at L is equal to 1, we are getting maximum. This photon carrying 1h cross, okay, just 1h cross, we are getting maximum. So that's what we are getting, and we were happy, and we concluded like OAM of photons manifests quite differently in quantum system compared to classical. Indistinguishability can be considered as unique feature of quantum mechanics like entanglement. So these were the conclusions, and I was writing the paper. Indistinguishable photons are a robust quantum system. This indistinguishability remains intact even after diffraction, therefore can be realized as a quantum resource in other information processing protocols. So that's what I was writing. Then Sarika went on leave, okay, while I was writing this paper, and after returning back from leave, she told, sir, wait, I will give you much better results. I will clean up the result. So this, she wanted to change the beam width and wanted to maximize this one thing here. But don't worry, I will give you much better result, then you write, okay. So after leave, she comes and started doing experiment. Now, she spent more than 2 months, she is not able to get this result. So again we are getting, now we are getting what we are getting. Suppose SPP2, so like classical, we are getting L is equal to 2 only in both the arms. Okay. So instead of 1, 1, now if you measure these photons which are being separated by beam splitter, if you measure their OM, it's coming 2 now. So there are certain conditions in the experiment in which it works as a OM mode, certain conditions in which it works as a photon, like photon carries the separately. So there are certain conditions, but we don't know which are the conditions when we get this result, when OM is distributed between photons and when it acts as a mode. This is the quantum experiment, Hango-Mandel interferometer. meter. So, but we don't know exactly what is happening. That's why I wanted to discuss this result. Okay. So, this is the crux, and for students I will tell, when you are doing any experiment, okay, make a sketch of the setup, take picture, write everything, what is the lens we are using, what is the mirror we are using, what is the focal length, everything you please write down, otherwise it becomes very difficult to repeat the experiment. You can see this example. It was coming repeatedly, but once he comes back, because some lens or some mirror, I don't know exactly, phases can play a very big role in optical experiments. Because even in HM, if you do the HM experiment, you are using beam splitter. That's what I showed you here. If you are using HM and this beam splitter, you just change the slight tilt. So instead of coalescence, you start getting anti-coalescence because of some phase factors are getting. So these are very tricky. So you have to write all the details of the experiment when you are doing experiment before you move on. Okay, so this is very important. And so we are not able to repeat this result, and that's why we are not able to submit this paper. And I want to have your feedback, that theory guys, what are the conditions which will, under which condition it behaves like photon distributes among themselves this circular momentum, and in which condition they are not able to distribute. So with that, I will, thanks for listening. Thanks.
About 10 minutes.
Yeah,
We will have enough time to
enough time, yeah.